Hello, my name is Karlo Jukic, and this is Lab 1. The purpose of this lab is to observe interactions between charged pieces of tape, determine how much excess charge is on one piece, and the magnitude of these forces. And we'll use the results to code a simulation to model and predict these charges and forces. However, our results is that the tape pieces have the same charge as each other as they were repulsive. The electric charge is 1.273 e to negative 8 coulombs, and deficient electrons were 8.44 e to the 10. Our fundamental principles is Newton's second law, which describes force relating to a particle or object's mass and acceleration, and Coulomb's law, which describes force resulting from presence of multiple point charges, where force of electric is equal to Coulomb's constant times the charge 1 and charge 2 multiplied over the distance between those charges squared times r hat, which is just direction of r. Our system setup and analysis is that the system is tape B, or the upper tape, the surroundings is tape A, or the lower tape, and initial conditions is the tape length of 0.2 meters, width of 0.02 meters, and mass of 0.0002 kilograms. Our analysis is that the distance between the pieces was 0.027 meters. We'll start our calculations with Fnet equal to Fg plus Fe, which is 0. Our force of gravity, which is just mass times gravity, the gravitational constant, which is just 0.002 meters per second squared, which is equal to the electric force. Going over the picture, we set our electric force equal to the Coulomb equation and isolate Q to find our charge. Plug in our values down here, and we get our charge being 1.273 e to negative 8. We'll then go on to find the atoms in the tape, which is the surface area of the tape divided by a surface area of an atom, it's 1.3 e to the 17 atoms. Deficient electrons, which is the tape charge over the electric charge of an electron, which is 8.44 e to the 10 electrons, and the ratio of electrons to atoms, just being number of atoms over number of electrons, which ends up being 1 electron for every 1.54 e to the 6 atoms. For our glow script, we start with constants. Our Phys is our Coulomb constant, our gravitational constant, our tape measures, and our tape separation distance. We'll model the bottom tape and upper tape, only difference being the tape separation and the y. We'll just start our calculations. The r hat was not necessary. We'll have our gravitational force, which is the mass times the gravitational constant, put in a vector, making it negative as it goes down. And then our electric force, which is just the gravitational force as seen earlier. Use the same equation as earlier to isolate our Q, and then we'll model this also as a vector. Our result is this: our point charges with the electric force going up, gravitational force going down, our magnitude being 1.962 e to the negative 3 newtons, and our calculated charge being 1.26 e to the negative 8. Our assumption is that the tape is a point charge with all total charge centered. These calculations ignore air resistance, and the charge is evenly distributed. Our similarities is that the calculated values are incredibly close, but the differences being that this cannot represent the tape fully, as this is assuming that for our discussion, we'll have our what if questions. The first one being what if electrons had positive charge, protons had negative charge? And the answer would be that tapes would still repel as the charges would still be the same. However, the magnitude of the force may vary as the electric charge of an electron and proton have different magnitudes, so this might account for some difference. And our second question is why is it important to handle the charge tapes as low as possible? Answer is that these charges are temporary and transmittable, so if the tape is touched enough or for long enough, the charges could equilibrate in the tape and no longer cause a force between each other, as there's no gradient of force. So our conclusion is that charge is everywhere and can be more powerful than initially seen in our practice equations we do in class. When a charge is present, Newton's second law and Coulomb's law can easily model these forces these charges enact. Thank you for watching.